speed of light and the universe. You see, when we speak of light, we speak of something that is, how should I say, both simple and impossibly mysterious at the same time. Light, it travels, it moves through space at a very particular speed, always the same speed, and this constancy, this unwavering nature of light's velocity, it tells us something profound about the fabric of reality itself. Now, you might wonder, why does light travel at this speed? Why not faster? Why not slower? And this is a beautiful question, because embedded in this question is really the entire architecture of our universe. The speed of light, approximately 3 million meters per second in vacuum. This number is not arbitrary. It emerges from the very properties of space and time themselves, from what we call the electromagnetic properties of the vacuum. Imagine, if you will, that you are standing on a train platform. A train passes by and someone on that train throws a ball forward. To them, the ball moves at, let us say, 10 meters per second. But to you, standing on the platform, the ball appears to move at the speed of the train plus those 10 meters per second, yes? This is common sense. This is how velocities add in our everyday experience. But light does not obey this rule. And this was the puzzle, you see, the great puzzle that occupied many thoughtful minds. If you shine a flashlight while standing still, the light travels at a certain speed. If you shine that same flashlight while running very fast, or even while traveling on a spaceship at enormous velocities, the light still travels at exactly the same speed. It does not add your velocity to its own. This is strange, deeply strange, and yet it is absolutely confirmed by every experiment we have ever conducted. The constancy of light speed was first suspected through the work of James Clerk Maxwell, who unified electricity and magnetism into one elegant theory. His equations, these beautiful mathematical expressions, predicted that electromagnetic waves, which include light, should propagate at a specific speed determined only by the electric and magnetic properties of empty space. When he calculated this speed from his equations, it matched the measured speed of light. This was no coincidence, Maxwell realized. Light is an electromagnetic wave. And then came the famous experiment of Michelson and Morley in 1887, which tried to detect the Earth's motion through what they called the luminiferous ether, a hypothetical medium through which light was supposed to propagate, much like sound propagates through air. They reasoned that if Earth moves through this ether, light should travel at different speeds depending on whether it moves with or against Earth's motion. But their interferometer, their beautifully precise instrument, detected no such difference, none at all. Light traveled at the same speed in all directions, regardless of Earth's motion. This null result was puzzling, frustrating even, to many physicists of that time. Some proposed elaborate explanations, modifications of the ether theory, contractions of matter. But the simplest explanation, though it required abandoning our intuitions about space and time, was that the speed of light is truly constant for all observers, and there is no ether at all. Ether. You see, when we say that light always travels at the same speed regardless of the motion of the source or the observer, we are saying something radical about time and space themselves. They cannot be absolute. They must be flexible, relative, adjusting themselves to keep the speed of light constant for everyone. This was a revolution in thinking, a complete reimagining of the stage upon which all physical phenomena play out. And let me take you through a thought experiment, a Gedanken experiment, as we say. Imagine you are in a spaceship moving very fast, perhaps half the speed of light. You turn on a lamp inside your spaceship. The light from that lamp spreads out in all directions at the speed of light as measured by you inside the spaceship. Now, someone watching your spaceship from outside, from Earth perhaps, also measures the speed of that same light. And what do they find? The same speed, exactly the same. Not faster because your spaceship is moving toward them, not slower because it is moving away. The same. How can this be? The only way this can be true is if time itself flows at different rates for you in the spaceship compared to the person on Earth. Your clock, your heartbeat, the vibrations of atoms in your body, all of these run slower as measured by the person on Earth, and space itself contracts in the direction of your motion. A meter stick in your spaceship, pointing in the direction of travel, appears shorter to the outside observer. This is not an illusion, not a trick of perception. It is the actual structure of space-time. Moving clocks run slow. Moving rulers contract. These effects are tiny at the speeds we encounter in daily life, impossibly tiny, but at speeds approaching the speed of light, they become dramatic, undeniable. And there is something else, something equally profound. As you accelerate, as you try to approach the speed of light, something interesting happens. Your mass, in a sense, increases from the perspective of the stationary observer. It becomes harder and harder to accelerate you further. To accelerate you to exactly the speed of light would require infinite energy. This is why nothing with mass can ever reach the speed of light. The universe itself prevents it through this relationship between energy, mass, and velocity. Only things without mass, like light itself, like photons, can travel at light speed. In fact, they must travel at light speed. A photon, a particle of light, cannot be at rest. It is always moving, always at this cosmic speed limit, from the moment of its creation until the moment of its absorption. Now, you might ask, and it is a good question, why this particular speed? Why not some other speed? The answer lies deep in the structure of space-time itself. The speed of light, really, is better thought of as the speed of causality, the maximum speed at which cause and effect can propagate through the universe. It is the speed at which massless particles must travel, and it emerges from the geometry of space-time. In the mathematics of relativity, space and time are woven together into a four-dimensional fabric. 3 dimensions of space, one of time. And in this four-dimensional space-time, there is a kind of geometry, a way of measuring distances and intervals. The speed of light is the conversion factor between space and time in this geometry. It tells us how much space is equivalent to how much time. 1 second of time corresponds to 299,392,358 meters of space in terms of this fundamental geometry. Think of it this way. We often ask, how far away is something? We might say, oh, the next town is 30 kilometers away, but we could equally well say it is 20 minutes away by car. We are mixing space and time, but using the speed of our car as the conversion factor. In the fundamental fabric of the universe, the speed of light is that conversion factor. It is the speed at which the universe itself operates, the speed at which causality propagates, the speed at which information can travel. And this has consequences, profound consequences for how we understand the universe. When we look out into space with our telescopes, we are also looking back in time. The light from the moon takes about 1¼ seconds to reach us, so we see the moon as it was 1¼ seconds ago. The sun's light takes about 8 minutes, so we see the sun as it was 8 minutes ago. If the sun were to suddenly disappear, we would not know it for 8 minutes. We would continue to see it, to feel its warmth for those 8 minutes until the last light it emitted reached us. The nearest star beyond the sun, Proxima Centauri, is about 4.24 light years away. When we observe it, we see it as it was 4.24 years in the past. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light years away. The light we see from Andromeda today left that galaxy 2.5 million years ago, when our ancestors on Earth were just beginning to use stone tools. And when we look even deeper into space with our most powerful telescopes, like the Hubble Space Telescope or the newer James Webb Space Telescope, we see galaxies so distant that their light has been traveling toward us for billions of years. We see these galaxies as they were when the universe was young, when stars and galaxies were just beginning to form out of the primordial hydrogen and helium. This is one of the beautiful things about astronomy, you see. We can directly observe the history of the universe. We cannot travel back in time, but we can look back in time simply by looking far enough away. Every observation of a distant object is an observation of the past, and this gives us a kind of cosmic archaeology, a way to study the evolution of the universe across billions of years. When astronomers look at galaxies at different distances, they are seeing them at different ages, different stages of development. Nearby galaxies appear as they were relatively recently, perhaps a few million or tens of millions of years ago. Distant galaxies appear as they were billions of years ago, when the universe was younger, when conditions were different. And because the universe is so vast and the speed of light is finite, there are parts of the universe we can never see. There is a cosmic horizon determined by how far light could have traveled since the beginning of the universe. The universe is approximately 13.8 billion years old, so one might think we could see objects up to 13.8 billion light years away. But it is more complicated than that because the universe has been expanding all this time. The most distant objects we can observe are now about 46 billion light years away, even though the universe is only 13.8 billion years old. This is because while the light was traveling toward us, the space between us and those objects was expanding, stretching, so the observable universe has a radius of about 46 billion light years. And anything beyond that we cannot see, not because our telescopes are not powerful enough, but because the light has not had time to reach us yet. Before we continue, I'd like to ask you to subscribe to the channel to help me reach the first 1,000 subscribers here. The purpose of this channel is to help you fall asleep with high quality knowledge, right? It doesn't cost anything. Just hit that subscribe button. Now, this expansion of the universe, it is a fascinating phenomenon in itself. When we say the universe is expanding, we do not mean that galaxies are simply moving apart through space like marbles rolling away from each other on a table. Rather, space itself is expanding, carrying galaxies with it. Imagine, if you will, an infinite sheet of rubber with dots marked on it. As you stretch the rubber, the dots move apart from each other, not because they are sliding across the rubber, but because the rubber itself is stretching. This is similar to what happens in our universe. The fabric of space itself is expanding, and galaxies are like markers in this fabric, moving apart as space expands. And here is something remarkable, something that surprises many people. This expansion is not limited by the speed of light. The speed of light limits how fast things can move through space, but it does not limit how fast space itself can expand. In fact, the most distant observable galaxies are receding from us at speeds greater than the speed of light because of the expansion of space between us and them. This does not violate relativity because the galaxies are not moving through space faster than light. Rather, space itself is expanding. It is a subtle but important distinction. This expansion was first discovered by Edwin Hubble in 1929, building on observations by Vesto Slipher and theoretical work by Georges Lemaitre and others. Hubble observed that distant galaxies showed a redshift in their light, meaning their light was stretched to longer, redder wavelengths. And the farther away a galaxy was, the greater its redshift. This relationship, now called Hubble's law, showed that the universe is expanding uniformly, with more distant galaxies receding faster. The redshift itself is a consequence of the Doppler effect, which you may be familiar with from sound waves. When an ambulance approaches you, its siren sounds higher in pitch, and as it moves away, the pitch drops. This is because the sound waves are compressed in front of the moving ambulance and stretched behind it. Light waves behave similarly. If a source of light is moving away from you, its waves are stretched, shifting toward the red end of the spectrum. If it is moving toward you, the waves are compressed, shifting toward the blue. But in the case of cosmic expansion, the redshift is not primarily due to galaxies moving through space. It is due to the expansion of space itself, stretching the light waves as they travel. The light was emitted at a certain wavelength, but by the time it reaches us, space has expanded, and the wavelength has been stretched proportionally. The more the universe has expanded during the light's journey, the greater the redshift. This discovery of the expanding universe revolutionized cosmology. It meant the universe had a history, a beginning. If we run the expansion backward in time, the universe must have been smaller in the past, denser, hotter. Extrapolating all the way back, we arrive at a moment of extreme density and temperature, what we now call the Big Bang, though I must say the name is somewhat misleading. It was not really an explosion in the conventional sense, not an explosion into pre-existing space. Rather, it was the beginning of space and time themselves, an expansion of space from an incredibly dense, hot state. The evidence for this hot, dense early universe is compelling. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, a faint glow of light coming from all directions in the sky. This radiation is the cooled remnant of the intense heat from the early universe. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, filled with a plasma of charged particles that scattered light. But once neutral atoms formed, light could travel freely for the first time. This first light has been traveling through space ever since, stretched by the expansion of the universe from visible light into microwaves. This cosmic microwave background is remarkably uniform, showing that the early universe was extremely homogeneous, but it is not perfectly uniform. There are tiny fluctuations in temperature, about 1 part in 100,000, and these tiny fluctuations are the seeds from which all structure in the universe grew. Regions that were slightly denser than average had slightly stronger gravity, attracting more matter, becoming even denser. Over millions and billions of years, these tiny fluctuations grew into the galaxies, galaxy clusters, and vast cosmic structures we see today. The Wilkinson Microwave Anisotropy Probe, or WMAP, and later the Planck satellite, have mapped these fluctuations in exquisite detail. From these maps, we can learn about the composition, age, and geometry of the universe. We find that ordinary matter, the atoms that make up stars and planets and ourselves, constitutes only about 5% of the total energy content of the universe. About 27% is dark matter, a mysterious substance that exerts gravitational influence but does not emit or absorb light. And about 68% is dark energy, an even more mysterious component that seems to be causing the expansion of the universe to accelerate. Dark matter was first inferred from the rotation of galaxies. When astronomers measured how fast stars orbit in galaxies, they found that stars far from the galactic center were moving much faster than expected based on the visible matter. There must be additional invisible matter providing the extra gravity to hold these fast-moving stars in their orbits. This dark matter forms vast halos around galaxies, and its gravity shapes the large-scale structure of the universe. Dark energy is even more puzzling. In 1998, two teams of astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is not slowing down, as one would expect from the gravitational attraction of matter. Instead, it is speeding up. Some force, some energy, is pushing space apart, counteracting gravity on cosmic scales. We call this dark energy, but we do not really know what it is. It might be a property of space itself, a cosmological constant, as I once proposed and then later called my greatest blunder, though perhaps it was not a blunder after all, or it might be some dynamic field, something that changes over time. The nature of dark energy is one of the great mysteries of modern cosmology, and it has profound implications for the future of the universe. If dark energy continues to drive accelerated expansion, galaxies beyond our local group will eventually recede so fast that their light can never reach us. The observable universe will shrink over time. Trillions of years in the future, intelligent beings looking up at the night sky might see only the stars of their own galaxy, with no hint of the broader cosmos beyond. But let us return to light, to photons, these massless particles that always travel at the cosmic speed limit. These photons, they are remarkable little messengers, carrying information across the vastness of space. A single photon emitted from a distant star billions of years ago can travel unimpeded through the near perfect vacuum of space, crossing unimaginable distances until it happens to strike a detector in one of our telescopes, or perhaps the retina of your eye. In that moment of absorption, after a journey lasting billions of years, that photon's existence comes to an end, and its energy is transferred to an electron in an atom, and we see. Think about this for a moment. Every time you look up at the night sky and see a star, photons that have traveled for years, decades, or even millennia are ending their cosmic journeys in your eye. You are connected, directly connected, to these distant suns through these particles of light. It is a profound connection, one that spans both space and time. Now, the nature of light itself, this is something that puzzled natural philosophers for many centuries. Is light a wave or is it a particle? This question occupied some of the greatest minds. Isaac Newton believed light was made of particles, which he called corpuscles. Christian Huygens proposed that light was a wave. Both had good reasons for their views, and both were, in a sense, correct. In the early 1800s, Thomas Young performed his famous double-slit experiment, which seemed to definitively prove that light was a wave. He shone light through two narrow slits and observed an interference pattern on a screen behind them, alternating bright and dark bands. This is characteristic behavior of waves. When two waves overlap, they can reinforce each other where their peaks coincide, creating bright bands, or cancel each other where a peak meets a trough, creating dark bands. This interference pattern was clear evidence of wave behavior. And yet, there were phenomena that waves could not explain. When light shines on certain metals, it can knock electrons loose from the surface. This is called the photoelectric effect. But here is the strange thing. The energy of the ejected electrons depends on the color, the frequency of the light, not on its intensity. Bright red light, no matter how intense, cannot eject electrons from certain metals, while even dim ultraviolet light can. This makes no sense if light is a wave. A wave's energy depends on its amplitude, its brightness, not its frequency. The explanation required a radical idea proposed by Max Planck and extended further in work on the photoelectric effect. Light, it turns out, comes in discrete packets of energy called quanta, or photons. Each photon carries an energy proportional to the frequency of the light. Higher frequency means more energy per photon. When a photon strikes an electron in the metal, it can transfer all of its energy to that electron in a single interaction. If the photon has enough energy, the electron escapes. If not, nothing happens, no matter how many low-energy photons you shine on the metal. So light is both wave and particle, or perhaps more accurately, it is neither and both. It is something that exhibits wave-like properties in some situations and particle-like properties in others. This wave-particle duality is one of the central mysteries of quantum mechanics, and it applies not just to light, but to all particles. Electrons, protons, even entire atoms can exhibit wave-like interference patterns under the right conditions. This quantum nature of light and matter is deeply counterintuitive. We are accustomed to a world where things are either particles or waves, not both. A thrown baseball is clearly a particle following a definite trajectory. A ripple on a pond is clearly a wave spreading out in all directions. But at the quantum scale, this distinction breaks down. A photon traveling through space is, in some sense, spread out like a wave, existing in a superposition of many possible paths. But when it interacts with matter, when it is detected, it always appears as a localized particle, transferring its energy all at once at a specific point. This is the famous measurement problem in quantum mechanics. Before measurement, a quantum system exists in a superposition of many possible states. After measurement, it is in one definite state. What happens during the measurement? How does the superposition collapse into a single outcome? This question has been debated for nearly a century, and there is still no consensus on the answer. Some interpretations say that the act of measurement causes a real physical collapse of the wave function. Others say that the wave function never collapses, but rather the universe splits into multiple branches, each corresponding to a different measurement outcome. Still others say that quantum mechanics is not a complete description of reality, that there are hidden variables we have not yet discovered. Each interpretation has its proponents and its difficulties. But regardless of interpretation, the predictions of quantum mechanics are extraordinarily accurate. It is the most precisely tested theory in all of science. When we calculate the magnetic moment of the electron using quantum electrodynamics, the theory of how light and matter interact quantum mechanically, we get agreement with experiment to more than 10 decimal places. This is astonishing precision, like predicting the distance from New York to Los Angeles to within the width of a human hair. And the speed of light appears here too, in quantum mechanics, in fundamental ways. The equations that describe how quantum fields evolve in time, the equations of quantum field theory, are constructed to be consistent with relativity. They respect the cosmic speed limit. Information cannot travel faster than light, even in the quantum realm. There was, for a time, some confusion about this because of what we call quantum entanglement. When two particles interact and then separate, they can become entangled, meaning their quantum states are correlated in strange ways. If you measure a property of one particle, you instantly know the corresponding property of the other particle, no matter how far apart they are. This happens faster than light could travel between them, which led some people to worry that entanglement might allow faster than light communication. But it does not. While the correlation is instantaneous, you cannot use it to send information. When you measure your particle, you get a random result. The other particle's measurement will be correlated with yours, but the person measuring that particle also gets a random result. Only when you come together and compare your results, traveling at speeds slower than light, do you discover the correlation. So no information travels faster than light. The speed limit is preserved. Entanglement is still deeply mysterious and counterintuitive, but it does not violate relativity. It tells us something profound about the nature of quantum reality, that particles that have interacted remain connected in some sense, their fates intertwined, no matter how far apart they become. As I once said, somewhat skeptically at the time, it is a spooky action at a distance. But experiments have confirmed it beyond doubt. Entanglement is real. This quantum nature of light has practical applications as well. Quantum cryptography uses entangled photons to create unbreakable codes. Quantum computers, still in their early stages of development, use quantum superposition and entanglement to perform certain calculations much faster than classical computers ever could. The quantum properties of light are being harnessed in new technologies, in precise sensors, in better microscopes, in gravitational wave detectors like LIGO, which detected ripples in space-time itself, using laser light to measure changes in distance smaller than the width of a proton. Speaking of gravitational waves, these are another prediction of relativity, another consequence of the finite speed of light and the structure of space-time. Just as accelerating electric charges produce electromagnetic waves, light, accelerating masses produce gravitational waves, ripples in the fabric of space-time itself. And these waves propagate at, you guessed it, the speed of light. When two black holes orbit each other, they lose energy by emitting gravitational waves, and they spiral inward, orbiting faster and faster until finally they collide and merge in a violent release of energy. The gravitational waves from such a merger spread out through space at the speed of light, stretching and squeezing space-time as they pass. When they reach Earth, billions of years later, they cause tiny oscillations in the distance between objects, oscillations that LIGO and other gravitational wave detectors can measure. The first detection of gravitational waves, announced in 2016, was a triumph of experimental physics and a confirmation of a prediction made a century earlier. It also opened a new window on the universe, a way to observe phenomena that emit little or no light, like colliding black holes or neutron stars. Gravitational waves travel through space completely unimpeded, you see. While light can be absorbed or scattered by dust and gas, gravitational waves pass through matter almost as if it were not there. They are incredibly difficult to detect, requiring instruments of extraordinary sensitivity. But once detected, they carry pristine information about the events that created them. We can now observe the universe not just with light, with electromagnetic radiation, but also with these ripples in space-time itself. It is as if we spent our whole lives watching silent films, and suddenly we can hear the soundtrack as well. And what these gravitational waves tell us, they tell us about some of the most extreme events in the cosmos. When two black holes merge, they create distortions in space-time so violent that they shake the very fabric of reality. The energy released in those final moments, as the black holes spiral together and merge, can exceed the light output of all the stars in the observable universe combined. Yet this energy is released not as light, but as gravitational waves, as vibrations in space-time. Black holes themselves are fascinating objects, predicted by the equations of general relativity. When a massive star exhausts its nuclear fuel, it can collapse catastrophically, compressing its core to a point where gravity becomes so strong that not even light can escape. The boundary beyond which nothing can escape is called the event horizon. Once something crosses the event horizon, it is lost forever to the outside universe. Even light, traveling at the cosmic speed limit, cannot escape from inside a black hole. At the center of a black hole, the equations predict a singularity, a point of infinite density where the curvature of space-time becomes infinite. But we must be cautious about taking this prediction too literally. When a theory predicts infinities, it is often a sign that the theory is being pushed beyond its domain of validity. General relativity describes gravity as the curvature of space-time, and it works beautifully on large scales. But at the extremely small scales and high energies near a singularity, quantum effects should become important. We need a theory of quantum gravity to truly understand what happens at the center of a black hole, and this is something we do not yet have. String theory, loop quantum gravity, and other approaches attempt to unify quantum mechanics with general relativity to create a theory that works on all scales, from the smallest to the largest. This is one of the great challenges of theoretical physics. At stake is our understanding of the Big Bang itself, which also involves extreme densities and curvatures, and perhaps the nature of space-time at its most fundamental level. But even without a complete theory of quantum gravity, we can observe black holes and study them. In 2019, the Event Horizon Telescope, a network of radio telescopes spread across the Earth, working together as a single instrument, captured the first image of a black hole's shadow. It showed the supermassive black hole at the center of the galaxy M87, some 55 million light-years away. The image revealed a dark region, the shadow of the event horizon, surrounded by a bright ring of glowing gas heated to billions of degrees as it swirls around the black hole before plunging in. This was a remarkable achievement, requiring careful coordination of telescopes on different continents, precise timing using atomic clocks, and sophisticated data analysis. The image confirmed predictions made decades earlier about what a black hole should look like. The shadow size matched the predictions of general relativity with remarkable precision. And at the center of our own galaxy, the Milky Way, there is also a supermassive black hole called Sagittarius AR, with a mass about 4 million times that of the Sun. We cannot see the black hole itself, of course, but we can observe stars orbiting around it, their motions governed by its immense gravity. By tracking these stars over many years, astronomers have mapped out their orbits and confirmed that there must be a massive compact object at the center. One star, called S2, has a highly elliptical orbit that brings it very close to the black hole every 16 years. At its closest approach, it reaches speeds of nearly 3% of the speed of light, fast enough that relativistic effects become measurable. These observations have provided some of the best tests of general relativity in the strong gravity regime. The precession of S2's orbit, the way its ellipse slowly rotates over time, matches the predictions of general relativity. If Newton's laws of gravity were exactly correct, the orbit would be a perfect, unchanging ellipse. But relativity predicts a small deviation, and this deviation has been observed. Now the universe is filled with light from all different sources, traveling at this cosmic speed. Stars emit light because they are hot. In the cores of stars, nuclear fusion reactions convert hydrogen into helium, releasing enormous amounts of energy. This energy gradually works its way out from the core to the surface, where it is radiated away as light and other forms of electromagnetic radiation. The sun, for instance, produces about 3.8 times 10 to the 26 watts of power, which is, well, it is an almost inconceivable amount of energy. The light from the sun's core, however, does not directly escape. It is absorbed and re-emitted countless times as it diffuses outward through the dense plasma. A photon created in a fusion reaction in the core might take hundreds of thousands of years to reach the surface, bouncing around randomly, absorbed and re-emitted in what is called a random walk. Only when it finally reaches the surface can it escape into space and travel freely at the speed of light. And when that light reaches Earth, just 8 minutes later, some of it is absorbed by plants through photosynthesis, converting light energy into chemical energy, building sugars from carbon dioxide and water. This is the basis of nearly all life on Earth. We are, in a very real sense, made of sunlight, made of energy that traveled from the sun and was captured by plants, which we or other animals then consumed. The atoms in our bodies were forged in stars, and the energy that powers our cells comes from the sun, mediated by the speed of light. Other stars, many vastly larger and more luminous than the sun, shine throughout the universe. When massive stars exhaust their fuel, they explode as supernovae, briefly outshining entire galaxies. These explosions scatter heavy elements into space, elements forged in the star's core and in the explosion itself. Carbon, oxygen, iron, all the elements heavier than hydrogen and helium, were created in stars and dispersed by supernovae. We are made of star stuff, quite literally. And across the cosmos, in distant galaxies, stars are being born and dying, shining their light into the void. Some of this light travels for billions of years before reaching our telescopes. When we observe a distant supernova, we are seeing a star that died long ago, perhaps before the Earth even formed. Its light has been traveling through space all this time at the speed of light until it reaches us. The universe is also filled with light we cannot see with our eyes. Our eyes are sensitive only to a narrow range of wavelengths, what we call visible light, from red to violet. But electromagnetic radiation spans an enormous range of wavelengths and frequencies. Radio waves have much longer wavelengths than visible light. Microwaves, infrared, these are also longer wavelengths. On the other side, ultraviolet light has shorter wavelengths than visible light, and then X-rays and gamma rays have even shorter wavelengths and higher energies. All of these are fundamentally the same thing, electromagnetic waves traveling at the speed of light. They differ only in wavelength and frequency, and different astronomical objects emit different types of radiation. Hot stars emit lots of ultraviolet light. Cooler objects emit infrared. The cosmic microwave background, as we discussed, is the cooled remnant of the Big Bang, now in the microwave part of the spectrum. Pulsars, rapidly rotating neutron stars, emit beams of radio waves. Supermassive black holes actively feeding on matter can emit powerful jets of particles and X-rays. To fully understand the universe, we need to observe it across the entire electromagnetic spectrum. This is why we have radio telescopes, infrared telescopes, ultraviolet and X-ray telescopes, often placed in space to avoid the absorption of these wavelengths by Earth's atmosphere. Each wavelength reveals different aspects of the cosmos. When we observe the universe in radio waves, we see things quite invisible to optical telescopes. We see the glowing clouds of hydrogen gas between the stars, tracing out the spiral arms of galaxies. We see the remnants of ancient supernovae, expanding shells of gas still shimmering with the energy of explosions that occurred thousands of years ago. We see pulsars, those remarkable lighthouses of the cosmos, neutron stars spinning dozens or even hundreds of times per second, sweeping beams of radio emission across space like a cosmic lighthouse. Pulsars were discovered quite by accident in 1967 by Jocelyn Bell Burnell, then a graduate student working with Anthony Hewish. She noticed strange, regular pulses of radio emission, so regular that they were initially jokingly called LGM1 for little green men, because the precision of the pulses seemed almost artificial. But soon it became clear that these were natural objects, neutron stars, the collapsed cores of massive stars left behind after supernova explosions. A neutron star is, well, it is an extraordinary object. Imagine taking the entire mass of the sun and compressing it into a sphere just 20 kilometers across. The density is so high that a teaspoon of neutron star material would weigh billions of tons on Earth. The gravity is so strong that the escape velocity from the surface is about half the speed of light. And these objects can spin incredibly fast because as the star collapses, conservation of angular momentum causes it to spin faster, just as a figure skater spins faster when pulling their arms in. The magnetic fields of neutron stars are also extraordinarily strong, trillions of times stronger than Earth's magnetic field. These magnetic fields channel particles and radiation into beams that emerge from the magnetic poles. If the magnetic poles are not aligned with the rotation axis, the beams sweep around like lighthouse beams as the star rotates. If Earth happens to lie in the path of one of these beams, we detect regular pulses of radio emission, one pulse per rotation. The most rapidly rotating pulsar known spins 716 times per second. Think about that for a moment. An object more massive than the sun, compressed to the size of a city, spinning 716 times every second. The surface is moving at a significant fraction of the speed of light. The forces involved are almost beyond comprehension, and yet these objects are stable, held together by the strength of nuclear forces. In the infrared part of the spectrum, we see through the dust that obscures much of the visible universe. Dust absorbs visible light but re-emits it as infrared radiation. This is why infrared telescopes like the James Webb Space Telescope are so valuable. They can peer into dusty regions where stars are being born, regions completely hidden from optical telescopes, they can observe the earliest galaxies whose light has been redshifted from visible wavelengths into the infrared by the expansion of the universe. The James Webb Space Telescope, launched in 2021, has already revolutionized our view of the early universe. It has observed galaxies that formed just a few 100 million years after the Big Bang, much earlier than we thought possible. These early galaxies appear surprisingly mature, surprisingly massive, which challenges some of our models of galaxy formation. How did such large galaxies form so quickly? This is a puzzle astronomers are now working to understand. Webb has also observed distant planets around other stars, analyzing the light that passes through their atmospheres to determine their composition. In the spectrum of this light, we can see the signatures of different molecules: water vapor, carbon dioxide, methane, and so on. We are searching for signs of potentially habitable worlds, places where liquid water might exist on the surface, where conditions might be suitable for life as we know it. In the ultraviolet and X-ray parts of the spectrum, we observe the most energetic phenomena in the universe. Hot gas swirling around black holes emits X-rays before it plunges past the event horizon. The corona of the sun, the hot outer atmosphere, is best observed in ultraviolet light. Ultraviolet observations also reveal hot, young stars and the regions of active star formation in galaxies. Gamma rays, the highest energy form of electromagnetic radiation, are produced in the most violent events in the cosmos. Supernovae produce gamma rays. Gamma ray bursts, the most energetic explosions known besides the Big Bang itself, can release more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. These bursts are thought to be produced by the collapse of massive stars into black holes, or by the collision of neutron stars. When directed toward Earth, even from billions of light years away, a gamma ray burst can be detected. Fortunately, these bursts are rare and highly directional. The gamma rays are focused into narrow jets, like searchlights. Only if we happen to be in the path of the jet do we see the burst. If a gamma ray burst occurred in our galaxy, pointed toward Earth, the effects could be catastrophic, disrupting the ozone layer and exposing the surface to lethal levels of solar ultraviolet radiation. But such events are rare, and the statistical likelihood of one occurring nearby and pointed at us in the near future is very small. All of this radiation, from the longest radio waves to the shortest gamma rays, all of it travels at the same speed, the speed of light. And this universality, this constancy, is part of what makes the speed of light so fundamental. It is not just the speed of visible light, but the speed of all electromagnetic radiation, the speed at which information propagates through electromagnetic fields. And underlying all of this is the structure of space-time itself, the geometry that determines how light travels, how gravity works, how the universe evolves. General relativity describes gravity not as a force in the traditional sense, but as the curvature of space-time. Massive objects like stars and planets curve the space-time around them, and other objects move along the straightest possible paths in this curved space-time, which we perceive as gravitational attraction. Light also follows these curved paths. This is called gravitational lensing. When light from a distant source passes near a massive object, like a galaxy or cluster of galaxies, its path is bent by the curvature of space-time. This can create multiple images of the background source or distort its shape into arcs and rings. Gravitational lensing is now a powerful tool in astronomy, used to map the distribution of dark matter, which we cannot see directly, but which reveals itself through its gravitational effects on light. The first observation of gravitational lensing was made in 1919 during a solar eclipse. Astronomers measured the positions of stars near the sun in the sky and found that they were slightly displaced from their normal positions. The sun's gravity had bent the light from these stars as it passed near the sun. This was one of the first experimental confirmations of general relativity, and it made headlines around the world. Now we observe much more dramatic examples of gravitational lensing. The Hubble Space Telescope has captured images of distant galaxies lensed by foreground galaxy clusters, creating beautiful arcs and rings of light. By studying the detailed shapes and positions of these lensed images, astronomers can infer the distribution of mass in the foreground cluster, including the dark matter that makes up most of its mass. Some lensing events are time variable. If a source like a quasar, a bright galactic nucleus powered by a supermassive black hole, is lensed into multiple images, and the quasar's brightness varies, we see that variation in each image, but at different times. This is because the light takes different paths, different lengths to reach us through the gravitational lens. By measuring these time delays, we can learn about the geometry of the universe and the expansion rate, providing an independent measurement of the Hubble constant. The Hubble constant, you see, it is a number that describes how fast the universe is expanding. It tells us the rate at which galaxies are receding from each other as space expands. But here is something curious, something that has puzzled cosmologists in recent years. Different methods of measuring the Hubble constant give somewhat different answers. When we measure it using the cosmic microwave background, analyzing the patterns in that ancient light, we get one value. When we measure it using local observations of supernovae and other distance indicators, we get a slightly higher value. The difference is small, but it is persistent, and it exceeds the uncertainties in the measurements. This discrepancy, sometimes called the Hubble tension, might be telling us something important. Perhaps our understanding of the universe's expansion history is incomplete. Perhaps there is some unknown physics at play, some component of the universe we have not accounted for. Or perhaps there are systematic errors in one or both of the measurement methods that we have not yet identified. This is an active area of research, and resolving this tension is one of the major goals of observational cosmology today. The expansion of the universe itself raises profound questions. Will it continue forever, or will it eventually reverse? The answer depends on the total energy content of the universe and the nature of dark energy. If dark energy remains constant, as current observations suggest, the expansion will continue accelerating forever. Galaxies beyond our local group will recede faster and faster, eventually crossing our cosmic horizon, disappearing from view as they recede faster than the speed of light due to the expansion of space. In this scenario, the far future of the universe is cold and dark. Stars will exhaust their fuel and die. New stars will cease to form as gas is used up. Galaxies will fade as their stars burn out. Black holes will slowly evaporate through Hawking radiation, a quantum process that causes them to emit faint radiation and gradually lose mass over incomprehensibly long timescales. Eventually, after perhaps 10 to the 100 years or more, even black holes will be gone, and the universe will be a cold, empty void, approaching absolute zero temperature. But this is so far in the future that the numbers become meaningless to human comprehension. The age of the universe now, 13.8 billion years, is nothing compared to these timescales. We live in a universe that is, cosmologically speaking, very young, still full of stars and galaxies and energy. There are other possibilities for the universe's fate, depending on the nature of dark energy. If dark energy is not constant but instead grows stronger over time, the expansion could accelerate more and more dramatically, eventually tearing apart galaxies, then stars, then planets, then atoms themselves in a catastrophic big rip. If dark energy weakens or reverses, the expansion could slow and eventually reverse, leading to a big crunch where the universe collapses back to a hot, dense state. But current observations favor the scenario of continued accelerating expansion. Now, let us think about what it means to travel at speeds approaching the speed of light. Suppose you could board a spaceship capable of reaching 99% of the speed of light. What would you experience? Time dilation would become very significant. For every year that passes on your spaceship, about 7 years would pass on Earth. You could travel to a star 100 light years away, and from your perspective, the journey might take only about 14 years due to time dilation. But when you returned to Earth, you would find that more than 200 years had passed. Everyone you knew would be long dead. You would be a traveler into the future, unable to return to your own time. This is not science fiction. This is the prediction of relativity, confirmed by countless experiments. Muons, subatomic particles created when cosmic rays strike the upper atmosphere, have very short lifetimes, only about 2 microseconds. At the speed they travel, they should decay long before reaching the ground. But they do reach the ground in large numbers because from our perspective, their internal clocks are running slow due to time dilation. They live much longer, as measured by us, than they would if they were at rest. GPS satellites orbiting Earth experience time dilation both from their motion and from being in a weaker gravitational field than the surface. If we did not account for these relativistic effects, GPS would quickly become inaccurate, with errors accumulating at a rate of about 10 kilometers per day. The fact that GPS works as well as it does is a everyday confirmation of relativity. If we could somehow travel at even higher speeds, closer to the speed of light, time dilation becomes even more extreme. At 99.99999% of the speed of light, time slows by a factor of more than 200. You could cross the galaxy, a journey of 100,000 light years, in what would feel to you like only a few hundred years, though 100,000 years would pass in the outside universe. This is the only way, within the laws of physics as we understand them, that interstellar travel could be feasible for human beings with our limited lifespans. But reaching such speeds would require enormous amounts of energy. To accelerate even a small spacecraft to a significant fraction of the speed of light would require energy comparable to the output of a large power plant running for years. And the faster you want to go, the more energy you need, increasing without limit as you approach the speed of light. This is the practical barrier to interstellar travel. We can imagine it, we can calculate what would be required, but the engineering challenges are immense. There are theoretical concepts for interstellar propulsion. Light sails, pushed by powerful lasers or by sunlight, could potentially reach a few percent of the speed of light. Nuclear pulse propulsion, using nuclear explosions for thrust, could perhaps reach higher speeds. Antimatter rockets, if we could produce and store antimatter in sufficient quantities, could be even more efficient. But all of these are far beyond our current capabilities, and even the most optimistic estimates suggest travel times of decades or centuries to reach even the nearest stars. The nearest star system, Alpha Centauri, is about 4.37 light years away. The fastest spacecraft we have ever built, the Parker Solar Probe, reaches speeds of about 190 kilometers per second at its closest approach to the Sun. That is fast enough to cross the United States in about 20 seconds. But at that speed, it would still take about 6,700 years to reach Alpha Centauri. To reach it in a human lifetime, we would need speeds at least 100 times faster, and that would still be only a small fraction of the speed of light. And yet, despite these challenges, despite the vast distances and the cosmic speed limit, there is something hopeful in the fact that the speed of light is finite. If it were infinite, if information could travel instantaneously across any distance, the universe would be a very different place. Cause and effect would lose their meaning. The arrow of time might not exist. The structure of space-time that allows for stable matter, for stars and planets and life might not be possible. The finite speed of light gives the universe a structure, a causal structure, where events are connected by light cones, regions of space-time that can influence or be influenced by a given event. Your past light cone contains all the events that could have influenced you, all the places from which light or other signals could have reached you by now. Your future light cone contains all the events you could potentially influence, all the places your light or signals could reach. Outside these cones are regions of space-time that are space-like, separated from you, events that are happening now in some sense, but which you cannot yet observe or influence, and which cannot yet observe or influence you. This structure, this causal architecture of space-time, it gives meaning to the concepts of past, present, and future. Without the finite speed of light, without this cosmic speed limit, the universe would lack this structure. Everything would be instantaneously connected to everything else, and the notion of causality, of one event leading to another in a definite sequence, would become muddled, perhaps meaningless. There is a deep connection here between the speed of light and the flow of time itself. In relativity, time is not something separate from space, not an absolute background against which events unfold. Rather, time is interwoven with space into a single entity, space-time. And the speed of light is the factor that relates spatial distances to temporal intervals in this unified framework. When we draw diagrams of space-time, we typically put time on the vertical axis and space on the horizontal axis. The world line of a stationary object is a vertical line moving forward in time, but not in space. The world line of a moving object is tilted, moving both forward in time and through space, and the world line of a photon, of light itself, is tilted at exactly 45 degrees if we choose our units appropriately, 1 unit of space per unit of time, moving at the speed of light. This 45-degree angle represents the maximum possible tilt for any world line, the maximum speed at which anything can move through space. Objects with mass have world lines that are steeper than 45 degrees, meaning they move slower than light. Only massless particles have world lines at exactly 45 degrees, and nothing can have a world line tilted more than 45 degrees, which would represent faster than light travel, because that would violate causality, allowing effects to precede their causes. Some people have speculated about faster than light travel using exotic solutions to the equations of general relativity. Wormholes, for instance, are theoretical tunnels through space-time that could connect distant regions. If a wormhole existed between Earth and a distant star, you might be able to travel through the wormhole and arrive at that star faster than light could travel through normal space between those 2 points. But creating or maintaining a traversable wormhole would require exotic matter with negative energy density, something we have no evidence exists in sufficient quantities, if at all. Similarly, there are solutions called warp drives, where space-time itself is contracted in front of a spacecraft and expanded behind it, allowing the spacecraft to effectively move faster than light relative to distant reference frames, even though locally it is not moving through space faster than light. But again, these solutions require exotic matter with properties we have never observed, and they may not be physically realizable. They are mathematical curiosities more than practical proposals. The speed of light, then, seems to be a genuine limit, not just an engineering challenge, but a fundamental feature of the universe. And perhaps this is appropriate. Perhaps the vastness of the cosmos, the great distances between the stars, are not meant to be easily bridged. Perhaps the universe is teaching us patience or humility or the value of cherishing the small corner of the cosmos we inhabit. Yet even as the speed of light limits how fast we can travel, it also connects us to the wider universe in profound ways. Every time we look up at the night sky, we are seeing into the past. The light from distant stars and galaxies has traveled across space for years, centuries, millennia, or even billions of years to reach us. We are observing ancient light, photons that began their journeys long ago, carrying information about the universe as it was. This gives astronomy a unique character among the sciences. A biologist studying animals observes them in the present. A chemist performing an experiment sees the results immediately, but an astronomer observing a distant galaxy is seeing that galaxy as it was millions or billions of years ago. We can observe the history of the universe directly, watching galaxies evolve over cosmic time, seeing how stars and structure formed, tracing the evolution of the cosmos from the Big Bang to the present. And when we turn our telescopes to the cosmic microwave background, we are seeing light that has traveled for 13.8 billion years, light that was emitted just 380,000 years after the Big Bang. This is the oldest light in the universe, the farthest back in time we can see with electromagnetic radiation. Before this moment, the universe was opaque, filled with a hot plasma that scattered light. The cosmic microwave background is the surface of last scattering, the moment when the universe became transparent for the first time. What happened before that moment? What was the universe like in those first 380,000 years? We can infer a great deal from theory and from indirect evidence. In the first few minutes after the Big Bang, the universe was hot enough for nuclear reactions to occur, fusing protons and neutrons into the light elements, hydrogen, helium, and trace amounts of lithium and beryllium. This process, called Big Bang nucleosynthesis, predicted the abundances of these elements, and when astronomers measured the actual abundances in old stars and pristine gas clouds, they matched the predictions beautifully. This is one of the key pieces of evidence for the Big Bang model. Even earlier, in the first second after the Big Bang, the universe was so hot that even protons and neutrons could not exist. Matter existed as a quark-gluon plasma, a soup of fundamental particles. And earlier still, in the first tiny fraction of a second, the four fundamental forces that govern the universe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force. As the universe expanded and cooled, these forces separated or froze out one by one. This very early universe is still largely mysterious to us. Our theories work well down to perhaps 10 to the minus 12 seconds after the Big Bang, when the universe was cool enough that our particle accelerators have probed similar conditions. Before that, we are extrapolating into unknown territory where our theories may not be reliable. And what about the Big Bang itself, the initial moment? Did time begin at the Big Bang, or was there something before? This is a question that stretches our concepts to their limits. In classical general relativity, the Big Bang is a singularity, a moment when density and temperature become infinite and the equations break down. Time itself may have begun at this moment, making the question, what came before, meaningless, like asking what is north of the North Pole. But quantum mechanics suggests that singularities may not be real, that something more subtle happens at these extreme conditions. Perhaps the universe bounced from a previous contracting phase. Perhaps it emerged from a quantum fluctuation in some pre-existing state. Perhaps our universe is one bubble in an eternally inflating multiverse. These ideas are highly speculative, but they represent attempts to push our understanding to the very beginning, to the ultimate origin. One of the more intriguing ideas about the early universe is cosmic inflation, a period of extremely rapid expansion that may have occurred in the first tiny fraction of a second after the Big Bang. During inflation, the universe expanded exponentially. doubling in size many times over in an inconceivably short period. A region smaller than an atom grew to perhaps the size of a grapefruit, or larger in about 10 to the minus 32 seconds. This is expansion far, far faster than the speed of light, but remember, this is the expansion of space itself, not motion through space, so it does not violate relativity. Why do we think inflation happened? Well, it solves several puzzles about the universe. One puzzle is the horizon problem. Different regions of the cosmic microwave background, regions so far apart that light could never have traveled between them in the age of the universe, nevertheless have almost exactly the same temperature. How did they come to be so similar if they were never in contact? Inflation explains this. Before inflation, those regions were close together in thermal equilibrium. Then inflation rapidly expanded space, pushing them far apart, but they retained their similar properties. Another puzzle is the flatness problem. The geometry of space, on large scales, appears to be remarkably flat, meaning that parallel lines remain parallel, and the angles of triangles sum to 180 degrees, just as in Euclidean geometry. But in general relativity, space can be curved, either positively curved like the surface of a sphere, or negatively curved like a saddle. For the universe to be as flat as we observe today, it would have had to be incredibly, extraordinarily flat in the early universe, fine-tuned to an absurd degree. Inflation explains this too. Any initial curvature would be inflated away, smoothed out by the exponential expansion, leaving space very flat, just as inflating a balloon makes its surface appear flatter from the perspective of an ant on the surface. Inflation also provides a mechanism for generating the tiny density fluctuations we see in the cosmic microwave background. These fluctuations arose from quantum fluctuations in the inflaton field, the hypothetical field that drove inflation. As space expanded during inflation, these microscopic quantum fluctuations were stretched to cosmic scales, becoming the seeds of all structure in the universe, the primordial perturbations that would grow through gravity into galaxies and clusters of galaxies. We do not yet know for certain that inflation occurred, but the theory makes specific predictions about the pattern of fluctuations in the cosmic microwave background. And so far, observations match these predictions quite well. Experiments are searching for more subtle signatures of inflation, such as particular patterns in the polarization of the cosmic microwave background, which would provide even stronger evidence. This is an active area of research, pushing the boundaries of observational cosmology. Now, in all of this, in all these discussions of the expanding universe, of the Big Bang, of cosmic inflation, the speed of light remains central. It is the cosmic speed limit, the maximum rate at which information can propagate. It determines our observable universe, the region from which light has had time to reach us. It structures causality, determining which events can influence which other events, and it appears in the fundamental equations that describe space-time, energy, and matter. There is a famous equation, perhaps the most famous equation in all of physics, that connects energy and mass through the speed of light. E equals mc squared. Energy equals mass times the speed of light squared. This equation tells us that mass and energy are equivalent, two forms of the same thing. A small amount of mass contains an enormous amount of energy because the speed of light is so large, and when you square it, it becomes larger still. This equivalence of mass and energy is why nuclear reactions release so much energy. When hydrogen fuses into helium in the core of the sun, a small amount of mass, less than 1% of the original mass, is converted into energy. But because of that c-squared factor, this tiny mass deficit corresponds to an enormous energy release. This is what powers the sun, what has kept it shining for 4.6 billion years, and will keep it shining for another 5 billion years or so. This equivalence also means that energy has mass. A hot object has slightly more mass than the same object when cold because the thermal energy contributes to the mass. The difference is tiny, far too small to measure in everyday situations, but it is real. And in high-energy particle collisions, we routinely create new particles from pure energy. A photon, if it has enough energy, can transform into a particle-antiparticle pair, an electron and a positron, for instance. Energy becomes matter. This has profound implications for cosmology. In the very early universe, when temperatures were extremely high, particles and antiparticles were constantly being created from energy and annihilating back into energy. There was a kind of equilibrium, a soup of particles, antiparticles, and radiation, all interconverting. As the universe expanded and cooled, this process stopped, and most of the particle-antiparticle pairs annihilated, leaving behind a small excess of matter over antimatter. This tiny asymmetry, about 1 part in a billion, is why we have a universe made of matter today. If matter and antimatter had been exactly equal, they would have completely annihilated, leaving only radiation. Why was there this asymmetry? Why slightly more matter than antimatter? This is one of the great unsolved problems in physics. The known laws of physics do not predict such an asymmetry, or at least not one large enough to explain what we observe. There must be some additional physics, some process in the early universe that created this imbalance. Understanding this is crucial to understanding why we exist at all. The speed of light also appears in the equations governing the expansion of the universe. The Friedmann equations, which describe how the scale of the universe changes over time, involve the speed of light, along with the density and pressure of the contents of the universe and the curvature of space. These equations tell us how fast the universe expands, how that expansion rate changes over time, and what the ultimate fate of the universe will be. And when we observe distant supernovae, using them as standard candles to measure cosmic distances, we are using light that has traveled billions of years to reach us. The light from these supernovae is redshifted by the expansion of the universe, and by measuring both the distance to the supernova and its redshift, we can map out the expansion history of the universe. This is how we discovered that the expansion is accelerating, driven by dark energy. These observations, these measurements of light from distant objects, are only possible because light travels at a finite speed and carries information across the cosmos. If light traveled instantaneously, we could not look back in time, could not observe the history of the universe. If light traveled much slower, the universe would appear much smaller, and many distant objects would be beyond our horizon. The particular value of the speed of light, combined with the age and expansion rate of the universe, determines what we can observe and what remains forever beyond our reach. There is a poetic quality to this, I think. The universe reveals itself to us through light, through these massless particles that travel at the cosmic speed limit, carrying information from the farthest reaches of space and time. We are connected to the cosmos through these fragile messengers, photons that have crossed unimaginable distances to reach our eyes, our instruments. And in a sense, we are made of light, or rather, of frozen light. The mass of matter, according to E equals mc squared, is equivalent to energy. The energy is there, locked up in the mass, and if released, as in nuclear reactions or matter-antimatter annihilation, it manifests as radiation, as light and other particles. We are energy in a stable form, patterns of matter held together by forces existing temporarily in the long cosmic flow. When we think about the nature of reality at its deepest level, we come to recognize that light is not merely something that illuminates our world, but rather it is woven into the very fabric of existence. The photon, This peculiar entity that is both wave and particle carries no mass, yet possesses momentum. It experiences no passage of time, you see. From a photon's perspective, if we could speak of such a thing, its emission and absorption occur at the same instant. A photon that travels for billions of years across the cosmos experiences no time at all. Its journey from a distant galaxy to your eye is, from its own reference frame, instantaneous. This is one of the strangest implications of relativity. As you approach the speed of light, time slows down. At the speed of light itself, time stops completely. A photon exists in a kind of timeless state, a pure connection between emission and absorption, between cause and effect, with no duration in between from its own perspective. Of course, we cannot truly adopt the reference frame of a photon because the mathematics breaks down. The equations become undefined. But we can take the limit, we can see what happens as we get closer and closer to light speed, and we see time dilation increasing without bound. This timeless nature of light connects to deeper questions about the nature of time itself. What is time? Why does it flow in one direction? Why do we remember the past but not the future? These questions have puzzled philosophers and physicists for centuries. The equations of fundamental physics, for the most part, are time symmetric. They work equally well whether time runs forward or backward. And yet, in our experience, time has a definite direction. Eggs break but do not spontaneously reassemble. We age but do not grow younger. Entropy, disorder, increases over time in isolated systems. This arrow of time, as it is called, seems to be related to entropy and the second law of thermodynamics. In a closed system, entropy tends to increase, and this gives time its direction. The past is the direction of lower entropy, the future is the direction of higher entropy. But why was entropy low in the early universe? Why did the universe begin in such a special low entropy state? This is related to the question of initial conditions, of why the Big Bang was the way it was, and we do not fully understand it. Some physicists have suggested that the arrow of time emerges from the expansion of the universe. As space expands, there is more room for disorder, more possible configurations of matter and energy, and so entropy can increase. In a contracting universe, if such a thing existed, perhaps the arrow of time would reverse. But this is speculative, and the relationship between cosmic expansion and the thermodynamic arrow of time is not fully understood. Light, meanwhile, propagates through this temporal flow, carrying information from past to future, never the reverse. We can see distant galaxies as they were in the past, but we cannot receive signals from the future. The speed of light sets the maximum rate at which information can flow forward in time through space. It is, in a sense, the speed of causality, the speed at which the future unfolds from the past. And this brings us to another profound aspect of light and the speed limit it represents. In quantum field theory, which combines quantum mechanics with relativity, particles are understood as excitations of underlying fields that permeate all of space. The photon is an excitation of the electromagnetic field. Electrons are excitations of the electron field. Every type of particle has its corresponding field, and what we perceive as particles are really disturbances, ripples in these fields. These fields interact with one another according to precise mathematical rules, and these interactions must respect the cosmic speed limit. Information cannot propagate through a field faster than the speed of light. This constraint, built into the structure of quantum field theory, ensures that causality is preserved, that causes precede effects. When two particles interact, say an electron emitting a photon, we can visualize this as ripples in the electron field and electromagnetic field interacting at a point. The changes propagate outward from that point at or below the speed of light. Distant regions of the fields do not immediately know about the interaction. The information spreads at light speed, creating a light cone of influence. Of this picture of reality, with quantum fields permeating space and particles as excitations of these fields, is strange and abstract, but it is our best current understanding of how nature works at the fundamental level. And the speed of light is built into this framework in an essential way. It is not just a speed limit for objects moving through space, but a fundamental property of how fields interact, how information propagates, how reality updates itself from one moment to the next. There is something almost computational about this picture. The universe evolves according to rules, updating the state of quantum fields based on their current state and the laws of physics. And this updating proceeds at a maximum rate set by the speed of light. In a sense, the speed of light is the clock speed of the universe, the rate at which reality computes itself forward in time. This perspective raises intriguing questions. Is the universe, in some sense, a vast quantum computer calculating its own future state? Some physicists and philosophers have explored this idea, noting that any physical system that evolves according to deterministic rules is, in a sense, performing a computation. But whether this is a useful way to think about the universe or merely an analogy is debatable. What is clear is that the speed of light, this fundamental constant, appears again and again in our deepest theories of nature. It connects space and time, mass and energy, causality and information. It determines the structure of space-time, the behavior of particles and fields, the expansion of the universe, and the ultimate limits of what we can observe and what we can do. And yet, for all its importance, the speed of light is also, in a way, arbitrary. It is approximately 299,792,458 meters per second, but this number depends on our choice of units, meters, and seconds, which are human conventions. In natural units, which physicists often use, the speed of light is simply one unit of space per unit of time. This makes the equation simpler and emphasizes that the speed of light is not really about light specifically, but about the structure of space-time itself. In these natural units, asking why the speed of light has the value it does becomes a bit like asking why a meter is the length it is. It is a matter of definition, of choosing units. The deeper question is why space-time has the structure it does, why there is a finite maximum speed at all, rather than asking about the particular numerical value of that speed in some arbitrary unit system. And this structure, this existence of a cosmic speed limit, has profound consequences. It means the universe has a causal structure, a clear distinction between past, present, and future. It means that information cannot travel instantaneously, that there are light cones of influence. It means that simultaneity is relative, that different observers can disagree about whether two distant events occurred at the same time. It means that time and space are not separate absolutes, but aspects of a unified space-time that bends and flexes in the presence of mass and energy. All of this follows from the constancy of the speed of light, from the fact that light travels at the same speed for all observers, regardless of their motion. This one fact, confirmed by experiment, implies all of special and general relativity with all their strange and wonderful consequences. As we approach the end of our journey through these ideas, through these contemplations on light and the universe, I find myself returning to a sense of wonder at the elegance of it all. The universe operates according to principles that are, at their core, remarkably simple and beautiful. The speed of light is constant. Mass and energy are equivalent. Space and time form a unified fabric that curves in the presence of matter. From these simple principles, all the complexity and richness of the cosmos emerges. We live in a universe that is comprehensible, at least partially, Through observation, through experiment, through mathematical reasoning, we can uncover the laws that govern reality. We can trace the history of the universe back to moments after its beginning. We can peer out to distances so vast that the light has traveled for most of the age of the universe to reach us. We can predict eclipses centuries in advance, land spacecraft on distant worlds, detect gravitational waves from colliding black holes billions of light years away. And yet, for all we have learned, mysteries remain. We do not know what dark matter is, this invisible substance that makes up most of the mass of galaxies. We do not know what dark energy is, this mysterious force driving the accelerated expansion of the universe. We do not have a complete theory of quantum gravity that can describe what happens at the center of black holes or at the moment of the Big Bang. We do not know if our universe is the only one or if there are countless others beyond our horizon. These mysteries are not failures of science, but invitations. They remind us that there is always more to discover, more to understand. Each answer we find leads to new questions, deeper questions. This is the nature of knowledge, an endless frontier, always expanding, like the universe itself. And in pursuing these questions, we use light as our primary tool. Telescopes collect light from distant sources. Interferometers split and recombine light to detect tiny changes in distance. Spectrographs disperse light to reveal the composition and motion of celestial objects. Light carries information across the cosmos, and we have become skilled at extracting that information, at reading the messages encoded in starlight. Think of all the photons that arrive at Earth from countless sources across the universe. Most pass unobserved, absorbed by the atmosphere, scattered by clouds, falling on bare rock or ocean. But a tiny fraction strike our telescopes, our instruments, our eyes, and in those moments they connect us to the wider cosmos. A photon from a distant galaxy, created in the nuclear furnace of a star billions of years ago, ends its journey in your retina, triggering a cascade of chemical and electrical signals that result in the sensation of seeing a faint point of light in the night sky. There is something profound in this connection, something that speaks to our place in the universe. We are not separate from the cosmos, not mere observers looking at something foreign and distant. We are part of it, made of the same elements forged in stars, governed by the same laws of physics, connected by light to everything that is, was, or will be within our cosmic horizon. The finite speed of light means we can never have instantaneous knowledge of the universe. There is always a delay, a light travel time between an event and our observation of it. The moon as we see it is the moon as it was just over a second ago. The sun is 8 minutes in the past. Even the person across the room from you is seen as they were a few nanoseconds in the past, though this delay is imperceptibly small. We live in a universe where information takes time to propagate, where the present is always slightly out of reach, where we are surrounded by images of the past. But this is not a limitation, so much as it is a feature of reality, a consequence of the structure of space-time. It gives the universe its causal architecture, its temporal flow. It allows for stable matter, for chemistry, for life. A universe with instantaneous communication, with no speed limit, might not be able to support complexity, might not have the stability needed for stars and planets and living beings. So perhaps we should be grateful for the speed of light, for this cosmic speed limit that shapes our reality. It makes the universe knowable yet mysterious, connected yet vast, comprehensible yet endlessly surprising. It allows us to look back in time simply by looking outward in space, to observe the history of the cosmos, to trace our origins back to the Big Bang. And as you drift off to sleep, perhaps you can imagine yourself as a photon, traveling at the speed of light through the universe. From your perspective, no time passes. The moment of your emission and the moment of your absorption are the same instant. You connect two points in space-time directly, timelessly. You are pure motion, pure energy, a messenger carrying information across the void. You experience the entire cosmos from beginning to end as a single eternal now. Or perhaps you imagine yourself in a spacecraft traveling at nearly the speed of light, watching as time slows down, as distances contract, as the universe transforms around you. The stars ahead shift toward blue, their light compressed by your motion. The stars behind shift toward red, their light stretched. Time on Earth races forward while your own time crawls. You are a traveler between past and future, experiencing the malleability of space-time, the relativity of simultaneity. Or perhaps you simply imagine the universe as it is, vast and ancient and beautiful, filled with billions of galaxies, each with billions of stars, countless worlds, phenomena beyond imagining, and all of it connected by light, by these massless particles traveling at the cosmic speed limit, carrying information, energy, the very essence of electromagnetic interaction. You are part of this universe made of its substance, governed by its laws, connected to all of it through the light that reaches your eyes. The universe is not just something we observe, something out there separate from us. We are the universe observing itself, matter and energy, arranged in such a way as to become conscious, to think, to wonder, to ask questions about existence and meaning and origin. The atoms in your body were forged in the cores of stars and scattered by supernovae. The light you see was emitted by distant suns, traveling across space to reach you. You are made of star stuff. As Carl Sagan so beautifully put it, you are a way for the cosmos to know itself. And in this knowing, in this wondering, there is something transcendent. We may be tiny, fleeting beings on a small planet, orbiting an ordinary star in an unremarkable galaxy. But we can contemplate the infinite, can grasp the laws that govern the universe, can trace our cosmic heritage back to the Big Bang. We can look up at the night sky and see not just points of light, but distant suns, ancient photons, the history of the cosmos written in starlight. So as you close your eyes as sleep overtakes you, let these thoughts settle gently in your mind. The constancy of light, the fabric of space-time, the expansion of the universe, the quantum nature of reality. Let them wash over you like waves, like ripples in a field, carrying you toward rest. There is no need to hold on to them, no need to remember every detail. Just let the sense of wonder remain, the feeling of connection to something vast and ancient and beautiful. The universe is here, all around you, governed by elegant laws, filled with mystery and light, and you are part of it, a conscious pattern in the cosmic flow, a temporary arrangement of matter and energy that can think and feel and wonder. Rest now, knowing that the universe continues its grand expansion, that light continues its eternal journey through the void, that stars are being born and dying, that galaxies are dancing their slow gravitational dance across billions of years. Sleep well, dear traveler. May your dreams be filled with the light of distant stars, with the curvature of space-time, with the quiet beauty of the cosmos. Thank you for joining me on this journey through ideas about light and the universe. If you enjoyed this exploration, please subscribe to the channel and like this video so that others may find it and drift off to sleep while learning about the wonders of our reality. Until next time, may you rest peacefully under the same laws of physics that govern all things, connected by light to the infinite cosmos. Good night.